Hello guys, very happy morning to one of you. And guys, now we are just going to start one of the new and most interesting subject, that is called heat transfer. So generally in heat transfer at least 5 to 6 marks will come, or worst case scenario only 3 marks will come. But heat transfer is one of the most interesting subject in my point of view. Because why it means why? Because it's a baby of a mother. It means like a thermodynamics is the mother and baby is heat transfer. Okay, so most of the time the basics will be comes upon the thermodynamics. Because why it means while the video is going, I'll just explain each and everything according to the thermodynamics point of view. If you haven't seen any kind of thermodynamics video also, this entire heat transfer will be so much beneficial for you. Okay, so for in that case, you just don't confuse. And without wasting time, let's get started. And welcome to my channel. My name is Rengakum, and let us start. Okay, so the first thing you can see, we can just go according to the basic difference. You can see the basic difference between thermodynamics and heat transfer. So thermodynamics and heat transfer. So you can see thermodynamics is just a, it means you can see how to say, means it's thermodynamics only tells about how much heat is gained or how much heat is lost. It doesn't tells about transfer. It means from one body to other body how the transfer is struggling, like that generally the thermodynamics won't tell. But heat transfer, you can see 1000 degrees Celsius to 25 degrees Celsius, it has been transferred. So how much rate of heat has been just came out. Okay, with time and with the certain kind of assumption also, we are just going to tell about this. Okay, so you can see in this heat lost by the billet, it means in this lost by the billet, generally thermodynamics, that's it. The Q amount of heat lost is 87.5 megajoule. It means how to say, means okay, you can see heat lost by so much 8, it means let us say 800 megajoule. So it means you can see mc delta t, but here the time is that no, Q equal to mc delta t. So temperature is 25 degrees Celsius minus of 1000 degrees Celsius. So mass we know 2000 and is something 450. So whether you can see guys, it tells about the heat, it means time, no, time is not dependent. For example, how to say, means let us take the iron box. So for the first 1 minute, it means you can see the temperature will be 0 degrees Celsius, and certainly the temperature will be, for example, let us say 100 degrees Celsius. Okay, just for example. So after you switch off the iron box, you can see this it means this time period is how much. Let us mention it is 40 seconds. Okay, so after that you can see, while after you switch off the iron box, this 100 degrees Celsius will be there, and you can see the time period will be so much. Okay, not 0 degrees Celsius, let us room temperature 20 degrees Celsius. So you can see the time period will be so much, it means 20 degrees Celsius. So the time to reach this is 5 minutes. So you can see this tells about the time. But in it means in thermodynamics, it only tells how much amount of heat is gained. 100 degrees Celsius minus 20 degrees Celsius, it means into mass of the plate into the specific capacity of the plate equal to the Q. Okay, this is the entire thing. The heat is being transferred from the plate, it means work done equal to heat transfer, like that it is generally tell. And the same thing you can see, the same amount of Q has been rejected, but it doesn't tells about the time. You can see it 100 degrees Celsius to 80 degrees Celsius, the heat transfer will be so much higher. Okay, the heat transferring rate, it means coming outside will be so much high, heat transfer will be higher. Okay, but you can see from 80, it means from how to say, means okay, 100 to 40 degrees Celsius, the heat transfer rate will be so much higher. It means 100 joules of heat will be comes out, but 40 degrees Celsius to 20 degrees Celsius, only 20 degrees Celsius of the heat will come out. Okay, so I think so you can understand. Or let us suppose 100 degree to 80 degree, 100 joules of heat is coming outside, but from 80 to 60 degrees Celsius, 80 joules of heat is coming outside. From 60 to 40 degrees Celsius, only 30 joules of heat is coming outside. From 40 to 20 degrees Celsius, only 5 joules of heat is coming outside. So you can say, understand. So depending on the temperature also, the heat changes, and with respect to the time variation. Okay, this thing is called as heat transfer. Okay, just a basic thing I just explained. Okay, I think so you got the point. So let us go. Wait, I'll just drink some water, because my throat has been infected for nearly 4 days, so that's why I couldn't upload enough videos. So you can see, when two different systems are brought at, when two systems are at different temperature brought in contact, the heat transfer takes place. Thermodynamics deals with the amount of heat transfer from one equilibrium state to another equilibrium state. Units of heat transfer used in thermodynamics, joule per kg, this thing. Okay, you can say this entire thing is represent watt. Okay, it means you can say watt as joule per second. Okay, it means it comes across, it means applied also on the area also. Okay, I think so you can answer. So for example, let us mention this one. So this is the thing, okay. So the area is just 1 meter, okay. This is also 1 meter. So here degrees are 1000 degrees Celsius. So how much will be the heat transfer rate? Suppose the Q will be, let us assume 100 kilojoules. Now the same thing is considered in the width is same, but the area is different, okay. So you can see it is 10 meters. It is all 10 meters, but 1000 degrees Celsius. So how much amount of Q will be transferred? Q equal to 1000 joules into 10 times. So you can see how much amount of heat is been getting transferred. So it depends on the area also, okay. Heat transfer generally depends on area. Second one is time, okay. I think you got the point. This is heat transfer. So you can see the temperature after certain length of the time before equilibrium is achieved. Temperature distribution within the body. Mode of heat transfer also is so much important. Convection, conduction, radiation, different types of heat transfer is also very particularly applied here, okay. So you can see practical application of heat transfer to mechanical energy. Calculation of the thickness of insulation for pipes carrying steams from steam generator to steam generator. This is so design of condenser, design of furnace for the heat transfer process such as annealing, normalizing, tempering. So this is different kind of cooling. So a lot of things has been added. But in this mainly we are just going to cover only 5 chapters, okay. Basic concept we will just explain. Next one is conduction. So it means Cartesian, cylindrical and spherical. Third one is heat exchange. Heat exchange is so much important thing. And thermal radiation. And seventh one is convection. And later on we can go to the unsteady state as well as through fins. So fins are leastly asked, but I'll just cover the basic first 5, okay. Later on we will just have a good explanation of others. So let us start with the basic concept. Basic concept, we can say conduction. Conduction is a mode of heat transfer which is assured with diffusion of energy due to molecular activity. Molecules just, it means this is one person and this is one person and this is one person, okay. So I am just giving a sweet box to this person. I am just asking the A person to give to the D person. D is a person here. So what he does is he just takes this sweet box and I just gave the sweet box to A, and what he does, he takes the sweet box and give it to B, okay. But you can see the position is not changing, okay. And you can see the B is giving the sweet box to C and the C is giving the sweet box to D, okay. So you can see these are the molecules, okay. In the molecule generally the heat transfer is occurring, okay. That's it, okay. So whenever you just heats up, it means how to say, means you just heats up means this A molecules, this A body will just start to vibrate, okay. These are the things I'll just explain, okay. So you can see it is a diffusion of energy due to molecular activity, okay. So you can see whenever we are talking about conduction, there should be no macroscopic bulk motion. So no macroscopic bulk motion should be. Conduction can take place because any medium, solid, liquid and gas, okay. This I'll just explain. So conduction generally only with the solid, it's not solid, liquid, gas also. So for conduction the basic law is Fourier law of heat conduction, okay. This is the most important thing. Fourier law of heat conduction, okay. So Fourier law of heat conduction, you can see French mathematician 1822. Fourier law is based on experiments only. It can't be derived from the first principle, okay. Just a normal thing. So you can see what he had just given is heat flux in n direction. I think so you can see this one. I just think. So heat flux in n direction is directly proportional to temperature gradient, okay. Not directly temperature gradient, okay. So Q dot, it means small q dot directly proportional dou T by dou n, okay. I think so you can understand. So this smaller thing, it means heat flux equal to, this is a heat flux equal to heat flow rate divided by area, okay. Heat flow rate, it means Q dot divided by M. It means how to say, means I think so you got the point, okay. Area. So generally in every heat transfer, heat flux only we usually just consider, okay. So you can see next one from the basics, Q dot n equal to dou T by, and for simple only. So while you just mentioned this in it means equal to without proportionally, we'll just put a constant, okay. Q dot n equal to minus Kn dou T by dou of n, okay. I think so you can understand. So Q dot n is what? Capital Q n of A of n, okay. Just put here. It means Q dot n divided by A of n equal to minus Kn dou T by dou n, okay. Q dot n equal to minus Kn A of n dou T by dou of n, okay. Okay, I think so you can understand. So this is the main important thing. So you can see dou T by dou n is because temperature can vary in any direction. Dou T by dou n is invalid, which means that heat is varying only in a specific direction, okay. It means particular term. It means that it is also dependent on the direction also. So this direction, this direction, this direction. So you can see as the direction changes, the line also changes. So the direction also most important thing that we want to just see. Okay. So you can see Q dot is a heat flow rate in n direction, thermal conductivity in n direction, area of isothermal surface normal to the heat flow rate. Okay, dou T by dou n is n direction. Okay, now according to Clasier's statement, second law of thermodynamics, natural heat transfer takes place from higher temperature. That's definitely you would have known this one. Higher transfer to lower temperature. In the assumed direction of n direction is same as the heat flow. Dou T by dou n is always dou T by dou n is negative. Okay, because the heat is flowing out. Okay, negative sign indicates the Fourier law of heat conduction. To keep the heat transfer rate positive, it means to make our answer positive, we put the negative. That's it. Okay, that's the other basic explanation. So Q dot n equal to K of n, A of n, dou T by dou n. Okay, so you can see no 90 direction. So generally it means you can see the direction is going outside. Okay, so no need to confuse it, just a basic thing. Okay, so only we have just talked about specific direction. You can see x direction, y direction, z direction. So minus k of x, a of x, dou T by dou x. Okay, the dou n is any particular direction. Okay, this we have specified in x direction, x, y, z, both of the three directions. So you can see homogeneous medium. Okay, homogeneous medium we just take, and you can see isentropic. So in strength of metal also homogeneous only we consider, as well as the isentropic metal we just consider. So same here. Okay, I think so you got the point. So each and everything will be represented a minus. Okay, so what is thermal conductivity? Thermal conductivity is a property of medium. Thermal conductivity is ability of the medium to conduct the heat. Okay, how much ability of the medium to conduct the heat. Okay, so for example, if we take I'm just heating this, it means let us consider this. It means think this is an area, this area, this area. Okay, I'm just heating the area this side. Okay, will this wood have the capability to transfer the heat? It will be so much minimum. Okay, but whenever I just take a steel, okay, steel means okay, let us consider this ring. Okay, this is a steel ring. So if I heat this side, the heat transferring rate will be so much high, it will just come here so much quickly. Okay, so I think so you can understand. So how much ability each and every material that is tells about the thermal conductivity. Higher the K value, higher will be the heat conduction rate for a given isothermal area and temperature area. Okay, I'll just explain later on. Okay, units and dimension of thermal conductivity. So you can see Q dot is this. Okay, so what is the value of K? So this is a basic thing. K equal to watt per meters degree Celsius. Okay, so just a simple thing. It means it means you can say, so you will tell this. So again, what is the Q? Q is W per. Okay, so area is meter square and temperature is degree Celsius. Dou x in x dash in meter. Okay, cancel and we'll get the answer. Okay, so what is that? It means the SI unit. So what is the LKS unit? You can see this is M L T power minus 3 Q minus 1. Okay, so you can see for Q this is M L square T power minus 3, and this one is L square Q dot of L. Okay, just cancel and later you just make it sure. Okay, I think so you can answer. So mechanism of conduction in solids. Okay, you can see these are the lattice. Okay, generally by lattice vibration the heat transfer will occur. Okay, so in metal there are a lot of free electrons, but in non-metal there are no free electrons. So in metals, due to the free electrons the vibration also occurs, so a lot of heat is being transferred. Okay, high temperature high energy, lattice structure, so low temperature low energy. Okay, I think so can lattice vibration means phonons. Okay, so generally metals and non-metals. So free electron movement metals only. Okay, in metals only lot of free electron is there, so due to that only lot of conduction takes place. Okay, so next one you can see here, in metals you can see conduction lattice vibration. So two things will be there, so lattice vibration plus of free electrons. Okay, so you can see in lattice vibration contributes only 15%, but in free electron contribute to 85%. Okay, so Q dot conduction of metals, heat transfer I think so you go and understand. So for next one you can see for non-metals, Q dot of conduction equal to Q dot of lattice vibration. solids are composed of atoms bonded together in a periodic arrangement called lattice. Okay, in metals free electron are present. Okay, in metals free electron present, while in non-metals free electron are absent. Okay, so you can see in metals conduction takes place due to lattice vibration phonons and movements of free electrons. Okay, movement of free electrons plays a major role in the heat conduction through the metals. Okay, so in non-metals lattice vibration only comes under. Okay, so I think so you can understand. So you can see effect of temperature and thermal conductivity of solid. Okay, so for metals you can see whenever it means the temperature has been increased during the time, if temperature increases during the time in metals I'm saying, the lattice vibration increases but free electron movement decreases. Okay, I think so you can understand. Just a basic thing, temperature increase, lattice vibration increases and free electron movement decreases. Okay, so in it means in non-metals what will happen, q dot of conduction, lattice vibration increases. Okay, so whenever you just heat, lattice vibration increases. Okay, you can see on increasing temperature lattice vibration waves phonons increases. The increase in lattice vibration leads to restriction of the movement of free electrons. Okay, so on increasing temperature heat conduction due to lattice vibration waves increases but heat conduction due to the free electron decreases. Okay, so you can see guys, one side it increases when lattice vibration increases but in other side the free electron decreases. Okay, so you can see metals having free electrons has, hence thermal conductivity of a metal entirely decreases. Okay, I think so you can understand. So how the thermal conductivity of a metal decreases due to the free electrons. Okay, the free electron will restrict the movement of thermal conductivity. Okay, so non-metal doesn't have free electron, hence the thermal conductivity of a non-metal increases with the temperature. Okay, you can see this is the basic formula. K equal to k naught 1 plus of alpha t. Okay, this is a basic formula. I think so you can remember this one. K equal to k naught 1 plus of alpha t. So k naught is thermal conductivity of 0 degree Celsius and alpha is thermal efficiency, coefficient of thermal conductivity. K is thermal conductivity of T degree Celsius. Okay, so these are the extra things it means. Okay, so you can see K1 and K2. So we just compare K1 and K2 with respect to alpha. So what is the alpha when we compare with the two materials? Alpha is this one. Okay, alpha is K2 minus of K1 divided by K naught T2 minus of T1. Okay, so you can see for metals as temperature increases the thermal conductivity decreases. Okay, you can see this one is positive, each and everything is positive, but the main thing is you can see the K decreases. Since the K decreases, the alpha, it means the thermal conductivity also tends to be negative, it will be so much decreasing state. Okay, so but for non-metals you can see thermal conductivity increases. Okay, K, it means alpha, it means okay, thermal conductivity increases. So you can see the temperature coefficient of thermal conductivity is positive, it means it will be so much higher. But for metal the thermal coefficient of thermal conductivity, thermal it means temperature coefficient, so thermal conductivity is different and the temperature coefficient of thermal conductivity is different. Okay, so you can see for imaginary materials the thermal temperature coefficient of thermal conductivity will be 0. Okay, so the moment we saying the K is constant, the three things we just assume. If in question they have just given thermal conductivity is constant, the one is homogeneous and second one is isentropic and third is alpha equal to 0. I think so you can understand. So you can see next one. So you can see the next one is thermal conductivity of various solids at 300 Kelvin in watt per meter. I'll just zoom a little bit. Okay, so you can see diamond, it means at each and everything this is for only 300 Kelvin. So you can see in general metals will have high thermal conductivity due to presence of free electron. Yes, definitely. So you can see diamond, some people say it is a metal, I'll just explain. So okay, silver you can see 429, copper and gold and aluminum. See, aluminum only we generally use a lot of thermal insulation, lot of other thing also, iron and steel. So okay, so I'll just explain. So I think so you can understand. So you can see for non-metals you can see it's about ice is how much, only 2.2, plastic is only so much. So you can see each and everything is so much lesser. So you can see polyurethane rigid form, it means refrigerator, the dose we use polyurethane rigid form only 0.025. so the thermal conductivity for this is literally so much low. Okay, so you can see in general metals have very high due to presence of free electrons. Okay, so you can see thermal conductivity measures how much the material transfer heat. Okay, material transfer heat typically typically watt per meter Kelvin. So in metals it generally will be free electrons, easy, so which carries both heat and electricity. Okay, here the breakdown. Okay, so you can see silver applies the highest thermal conductivity among, okay, high efficient, it means high efficient free electron. So copper you can see heat sinks and pipes. Okay, next one you can see gold is lower than silver but still high, but offers electronics while corrosion, while we are using the corrosion is so much lesser. Okay, you can see aluminum is slightly brittle and allowing, but so we are just using a cookware, radiators, lot of things, we just use aluminum. So you can see silver greater than aluminum, copper greater than gold greater than aluminum. Okay, so cost you can see silver is so much costlier. Okay, so you can see how much one, it means 1500 kg, it means 1 kg goes around $1500. Okay, but you can see copper is approximately how much, 10 kg, it means 10 kg per kilo, it means dollars. Okay, $10 per kg, and gold is extremely high. Okay, wow, what is same, it means $1 lakh, okay, per kg. Aluminum is only cheapest, you can see only it means $2 per kg. So that's why we are using mostly aluminum. Okay, so next thing is at very low temperature the thermal conductivity starts low, yes, and rises to a peak. It means, so this thing, okay, I'll just, while we are just going to other thing, I'll just explain. Okay, so thermal conductivity of pure metal is always, when we compare with the poor metal will have higher thermal conductivity when we compare with the alloys. Okay, so you can see next one, non-metals has very less thermal conductivity due to absence of free electrons. Okay, so here it means generally they are used to decrease the heat flow. Okay, so you can see fire, clay, it means asbestos and furnace. So these are the things, asbestos and polyurethane from refrigerators. And why? Because you can see regularity of lattice arrangement plays an important role in energy transfers due to the lattice vibration bonds. So crystal material well ordered structures such as quartz. So quartz also so much important, guys. You can see quartz has higher thermal conductivity as compared to amorphous. It means glass is not a crystalline structure, it is an amorphous structure. Okay, so in next you can see non-metals such as diamond, beryllium oxide has higher. Okay, because why? Because why we are just comparing the diamond means, because diamond is a non-metal, it is not comes under the metal category, but due to the crystalline structure it has high thermal conductivity. Okay, that's it. So you can see crystalline metal well ordered structures such as quartz. Okay, whenever the crystalline structure is well ordered, so there will be higher thermal conductivity. Okay, amorphous is glass. Okay, so you can see except the good conductors, they are both are, it means generally good heat conductors are good electrical conductors except diamond and beryllium. Okay, so diamond and beryllium are bad conductor of electricity. Okay, so regularity of iron, so this is the thing. Okay, I think so you got the point. So next one you can see mechanism of conduction gases. Okay, later on we just see the conduction in liquids, now we can see about the gases. So you can see this side will be higher energy, this side will be lower energy. So it means upper and bottom side we just insulated. So okay, higher energy will be just transferred to the lower energy. Okay, next one you can see whenever they has the Boltzmann constant, means kinetic energy equal to 3/2 of k times of temperature. Okay, higher temperature the molecules have higher energy as compared to the lower temperature remains molecules. If molecules so you can see in higher temperature region molecules have higher energy as compared to the lower temperature region. If molecules move from higher temperature region to lower temperature, it creates a kinetic energy possessed by the lower, and due to the high random movement the kinetic energy is getting converted to collision. So here lot of collision will occur. Due to the collision here the heat transfer will be occurring. Okay, so I think so you can understand. So the conduction and the convection rate heat transfer depends on the molecular weight of gas. Yes, definitely. Okay, so each and everything depends on the molecular weight of the gas also. So kinetic energy equal to 3/2 of kT. Okay, so kinetic energy mv square divided by 2, when you cancel velocity equal to root of 3 kT of mass. Okay, you can see this is a molecular mass. So if molecular mass is more, means the velocity will be lesser, so definitely the heat transfer rate will be lesser. Okay, so you can see it means generally if higher velocity is being there, means the randomness will be more, and as well the heat transfer will be more. But you can see as the velocity is so much lesser, the randomness will be lesser, heat convection rate will be, and thermal conductor also will be lesser. Okay, so helium, hydrogen, helium, air. So you can see molecular mass of air is greater than molecular mass of helium is this, it means helium is 4 gram per mole, and hydrogen is 2 gram per mole. And whenever we just say kinetic energy, it means each and everything is independent, okay. So kinetic energy, it means if molecular mass is higher, the kinetic energy, it means thermal conductivity is lower. So therefore higher molecular weight, higher, lesser will be the velocity, and lower will be thermal conductivity due to lower diffusion collision, okay. So thermal conductivity of hydrogen is this one, helium, and air, you can see thermal conductivity of air is so much lesser, okay. Very low gas, hence gas are poor conductors of it, okay. So you can see thermal conductivity of air is this one, of water is this one, okay. So velocity equal to root of 3 times kT of m, okay. So temperature increases, velocity also increases, okay. So on increasing in temperature, the velocity of a molecule increases, randomness increases, leading to increase in thermal conductivity, okay. So you can see temperature increases, the thermal conductivity also, you can see the temperature increases, here each and everything is dependent, okay. The temperature increases, the thermal conductivity also will be increasing, okay. So I think so can understand. So you can see the thermal conductivity for hydrogen is so much higher. So when we just increase the temperature, the thermal conductivity also increases, okay. I think so can understand. So gas having higher molecular mass, hence lesser thermal conductivity, okay. I think so can understand. So next one you can see discussion on liquids. So how now we just seen about the gases. So when we just see about the liquids, how it's been changeable, okay. One second. So next one, liquids. So molecular condition associated with the liquid state are more difficult to describe in a physical. For explaining, so thermal conductivity of non-metallic liquid generally decreases with increasing temperature. So water increasing only increases, okay. So next one you can see for water, you can see this is the thing. So it means for certain limit you can see while we just increase the temperature, you can see the thermal conductivity increases, but after a certain limit the thermal conductivity starts to decrease, okay. So you can see for ice, it means at 300 Kelvin, ice is how much? 2.2 watt per meter Kelvin, okay. So it means for 1 meter, it just how to say means for 1 meter, it means while the temperature is being increased, it means temperature increases 1 degree Celsius, how much amount of heat is being transferred? So 2.2 joules per second of heat is being transferred outside, okay. So when we just compare about the silver, how much? Nearly 450. So watt per meter Kelvin, it means 1 degree Celsius rises, it means how much amount of it means heat is transferred? 450 joule per second of heat is being transferred outwards for 1 meter, okay. I think so you can understand. So you can see where is 450, where is 2.2, okay. I think so you got the point. So how much amount of temperature will be increasing, according to that the amount will be this transfer outside, okay. So okay, and means up to a certain limit. So after a certain limit, each and everything decreases. So generally the thermal conductivity of solid, yes, this is the most important thing. Thermal conductivity of solid is greater than thermal conductivity of liquid, greater than thermal conductivity of vapor, okay. So in liquids, liquid metal having maximum in liquids alone, liquid mercury has maximum thermal conductivity. Liquid metals such as liquid mercury has high thermal conductivity, hence they are used in a heat for operation during generally they are used in nuclear power plant, okay. So you can see this one is 8.43, okay. So next thing you can see convection. So convection is a mode of, until now we have just seen only the conduction. This is convection. Convection is a mode of heat transfer which is associated with the diffusion of energy due to molecular activity and energy transfer, okay. So in generally in the conduction only, it means molecular activity will be there, okay. Molecular activity, okay. No macroscopic, it means no bulk motion in the conduction will be, but in convection molecular activities, molecular transfer will also occur, and as well as the macroscopic bulk motion will also occur, okay. I think so you can understand. So you can see convection, molecular activity plus macroscopic bulk motion. So convection is conduction plus advection, okay. This is the most important. Convection equal to conduction plus advection, ADV advection, okay. I think you can understand. So you can see generally while we are just heating here, you can see the center molecule also will just transfer the heat energy, as well as the rotation, it means the circulation also will occur. So down molecule will just go to the upper molecules, and the upper molecule will come to the lower molecules, okay. So generally you can see here the temperature will be so much high, so density will become so much lesser. Okay, so it just goes up, and when you just see above, the temperature will be so much lesser, the density will be so much high, so it will come down. Okay, so temperature increases, density decreases. So macroscopic bulk motion, advection is macroscopic bulk motion. Okay, so whenever you just tilt it, you can see above this one. So generally cold, it means this will be lesser temperature and it will just stay here. So here it means while you just turn, entirely conduction only will occur. Okay, I think so you got the point. So convection equal to conduction plus advection, and if no macroscopic bulk motion, advection is 0. Okay, just a basic thing. So you can see in conduction also, so there are two type of convection, free convection and forced. Okay, generally when we just use the fan and blow, this is forced convection. Free convection means just we will just keep the hot molecule in the surface. Okay, if it means fluid motion takes place due to density difference, it is free convection. Okay, if it is by external agency like fan or blow, it is called as forced convection. Okay, so generally during the morning time, the girls will use the hair dryer. So generally means the water molecule should go outside, that also comes under force convection. Okay, next one is Newton's law of cooling. So in generally conduction, what will be the conduction goes upon Fourier's law of heat transfer, but in convection generally Newton's law of cooling. Okay, I think you got the point. So you can see generally what will happen. Suppose if the plate temperature is 100 degrees Celsius and surrounding is 20 degrees Celsius, I mean where the heat will just flow from plate to the outer atmosphere, it will go. Suppose if the surrounding temperature is 100 degrees Celsius, the plate is 20 degrees Celsius, means where the heat will come from surrounding to the plate will come. Okay, I think so I can understand. So that's why they call T infinite, and it means this one TW is the plate temperature, T infinite is the air temperature. Okay, so contact area generally. Okay, so next one you can see heat flux in that, it means before time what we just put in Fourier's law, heat flux directly proportional dou T by dou N. Okay, but here it in convection what will be Q heat flux equal to directly proportional to temperature. Okay, Q dot of temperature difference. Okay, del T. So you can see, I think so you can understand. So while we just elaborate, it means Q dot equal to H of X del T. Okay, Q dot is capital Q divided by area. So Q dot divided by area equal to H of X of del T. So Q, it means capital Q is H of X area of X of del T. Okay, this is the basic thing. Okay, I think so you can understand. So generally you can see H of X is local, it means at the particular area. You can see this at this particular area, but generally we take average. Okay, H of H means H bar is average. Okay, average heat transfer coefficient. Okay, so it is also called as film conductivity. Okay, average heat transfer or film conductivity also we just represent them. Okay, so general basic thing. Okay, this I'll just explain later. Okay, so Q dot is this one, H bar A of delta T. Okay, H bar equal to Q dot of A of delta T. Okay, W will be meter square dot degree Celsius. Okay, basic this here meter square will come, but in thermal conductivity only meter will come. Okay, this is a basic thing. Okay, so this is the unit. Okay, so next one we can see. So this I'll just it means this I need a lot of a good explanation based across this. Okay, so okay, let us explain. So you can see this is the entire temperature profile. Okay, so here two things are considered. Okay, suppose this is the thing. Okay, so I think so in fluid mechanics you would have known about the boundary layer theory. So here the U will be 0, velocity will be 0, while it just goes on increasing, the velocity will be increasing. The same here when we compare thermal boundary layer, it means temperature. This is velocity boundary layer, this is temperature boundary layer. You can see at the it means like this it will be. So it means the temperature 100 degrees Celsius and the plate is only 20 degrees Celsius, means so you can see 100 is increased to give the plate 20. So at the beginning the temperature transfer will be, heat transfer will be so much higher, but after all it just reaches to certain 100 degrees Celsius. Okay, this is a basic thing. Okay, so here the temperatures depend on entirely Y, it means Y axis. Okay, I think so got the point. So here this is a thermal, it means velocity boundary layer, hydrodynamic boundary layer, but here this is a thermal boundary layer. Okay, I think so you got the point. So in this thing both conduction and as well as convection will also occur. Okay, I think so you got the point. So here the both conduction as well as the convection will also occur. Okay, so you can see, I'll just zoom a little bit. Okay, so okay, you can see here. So here the entire above the fluid will be in a hot temperature, okay. So you can see here 50 watts per meter cube is being transferred. So simultaneously you can see in the fluid also the temperature changes will also occur. So heat flux conducted through stationary fluid layer equal to heat flux conducted to the moving fluid layer, okay. So how to say means so you can see this one, it means here what I just told, the hydrodynamics, here the velocity will be 0, okay. So I'll just represent it here, entire thing u will be 0, okay. Suppose I'll just represent here, so you can see u will be 5 meter per second, okay. So suppose you can see here this top layer is attached with this plate layer, the plate is also u 0, okay. From this u 5 meter per second the heat transfer will occur, okay. I think you are getting the point. So here as the u is 0, this is no moving is occurring, so this will consider as a conduction, okay. So you can see from molecular to molecular the heat transferring occurring, okay. It means you can see guys, this is a moving fluid, okay. From moving to stationary, heat transfer is occurring, okay. I think so you got the point. So that's why they are mentioned here. So you can see heat flux conducted through stationary fluid layer equal to heat flux conducted to moving fluid layer, okay. So top one is moving, bottom one is stationary, okay. So k minus k of f dou t by dou of y tends to 0 equal to h of x of del t, okay. So it means q dot of conduction equal to q dot of convection, okay. Dou minus k of x dou t by dou x y tends to 0 h of x of del t, okay. I think so again. So h of x is just put here minus k of x dou t by dou x y tends to 0 divided by del t, okay. So next thing you can see guys, here u is 0, it means this u is 0, and as well as the plate, this is a plate, the plate is also velocity is 0, okay. So you can see here both are conduction, okay. This also conduction, this also conduction. So minus k of a fluid dou t by dou x of fluid equal to minus k of solid dou t by dou of x of solid, okay. I think so again, everything y tends to 0, okay. I think so you got the point. So you can see about this one. So general value of average heat